Math 265A, Quest to College. I'm Joe Vasta, and we are going to cover 3.2, the derivative as a function. So we kind of already know how to do some of the problems in 3.2 because of the approach we took in 3.1. I'm going to go ahead and crank out the derivative of this using the definition with the difference quotient. And this is what you'll be doing in 3.2 along with some other stuff. So how do we find the derivative of this? The derivative is the limit as h approaches 0 of the difference quotient. So that is what the limit is. The derivative is, it's the limit. And this tells us the slope of the function. It's also a velocity function and a rate of change. So what we're going to do is start off by figuring out dq. So now would be a good time to pause the video to see if you can find the derivative of this function. The first part is dq. Okay, dq is this guy right here. This is dq. So what I'm doing is sort of a review from last time. I'll write out dq again. This is the hardest part of this problem, is computing dq and simplifying. Okay, f of x plus h. So everywhere there's an x, I'm going to put an x plus h. So that's that first part. I'll color code it like I've been doing on some of them. So that became that. Okay, I'm going to go ahead and go subtract. We have f of x, which is this right here. X plus 2 over 3x. And this one will be in this lime green color. This is all over h. Okay, so what we need to do on top is get a common denominator. That common denominator is going to have a 3 in it, an x plus h package, and also an x. So I see that the one on the left, the fraction on the left, needs an x. So I'll just put the x right there, multiply top and bottom of that fraction by x. This fraction over here needs one of these guys right here, the x plus h packet. So we multiply top and bottom by that. Let's go ahead and continue this on another piece of paper here. So what do I have? Well, on the top, I'll just write it all out. So this equals x plus h plus 2 times x minus. Okay, so there's something I should have done over here and I didn't. I need to put parentheses around that x plus 2. So I have x plus 2, quantity x plus 2, times quantity x plus h. This is all over 3x x plus h, all over h. Okay, so we're computing the difference quotient, and then we'll take a limit. That will be fairly simple. It's this computation that's a little bit trickier. Okay, so now on the top, I'm going to go ahead and distribute the x. So I'll have x squared plus hx plus 2x. Okay, so that's that one right there. I'll keep the minus there, and then we'll have a FOIL, which is first x squared outside hx, keeping things alphabetical. Inside 2x last 2h. This is all over 3x x plus h all over h. Now some of you may have noticed up at this step, I didn't say it, but I better just say it. Some of you may have noticed, hey, let's cancel the x plus h's here. Well, you can't do that because in order to cancel something, to reduce a fraction, you need one term on the bottom, which you have. That's one term. You need one term on the top. Terms are separated by pluses and minuses. You actually have two terms on the top. This is the first term. That's the second term. Because there are two terms on the top, you cannot cancel. So we go ahead and multiply things out. Let's go ahead and distribute that negative. So this is x squared plus hx plus 2x minus x squared minus hx minus 2x minus 2h. And we're just going to keep copying the same thing here. And then this is all over h. This does require a lot of pieces of paper. Before we move on to the next piece of paper, we notice up here that the x squareds can cancel, or you combine them and they're 0. And same with the hx and the negative hx. Anything else like that? Well, I have to say the 2x and the negative 2x can also go away. So you're just left with a negative 2h on the top of the top fraction, or the numerator of the numerator. So what I'm going to do is I'm going to do a copy dot flip, where I copy the top, dot is multiply, and then flip the bottom. Other teachers might call it an invert in multiply. So let's see what we have here. So this equals copy, which is negative 2h all over 3x x plus h dot, there's the multiply, and then flip that, 1 over h. I do have one term on the top and one term on the bottom, because it's all multiplied. I know this factor within this one term has two terms in it, but the big picture, there's one term on the bottom. Let's go ahead and cancel the h's. And what I end up getting is I end up getting the difference quotient. So the difference quotient is negative 2 on the top, and on the bottom, 3x x plus h. So that's dq. It's not my final answer, but I'm almost there now. Okay, so what we want to do, we'll get rid of this work here. So we want to compute the derivative. So we'll put that there, put that right there. Now remember, the derivative has this notation, f prime x, this equals the limit as h approaches 0 of dq. So we've done these a lot of times, and now we know how to take a limit. So when I take the limit, let me just write it out. I was going to be lazy. I better just write this out. Of dq. So here's dq. Okay, well, we've practiced limits in the last chapter, and with this we just replace the h with a 0 and hope nothing bad happens, and nothing bad will happen in this example. You'll have a negative 2 on the top And this will just become an x here in the parentheses, so this will be 3x squared. So it looks like I am done. F prime, the derivative is -2 over 3x squared. So there's the answer. Okay, so now we're going to point out a few things. So what we did wasn't new. We've done this before in 3.1, and we even did this on one of the bug handouts with derivatives. If this function was written so it said y equals instead, which is legitimate, and they didn't call it a function name like f, well, there is notation for the derivative when it just says y equals an expression. And that notation then would be y prime instead of f prime of x. So y prime is another notation. So we're going to come back to this example, okay? Because we're finished with the example, but I'm going to show you some graphs on this example. But before we do that, I think we should look at other notations of the derivative, because they will pop up from time to time as you do calculus. So let's go take a look at my definition sheet here. Once again, I save a lot of time in lecture by having this all typed out. You know, in class, I would be writing this all on the board. Okay, the derivative of f of x is f prime of x. There's the limit of the difference quotient as h goes to 0. The derivative is also called the slope function, the velocity function, and the rate of change function. There's probably other names as well. Okay, but we've kind of learned what the derivative is by velocity. That was our approach with the bugs. But now we're saying, hey, the derivative, this f, is just a function. Other notations. I don't know why this one's in there. This is the notation I used up here. Oh well, I'll just keep it there. Other notations would be, okay, yeah, I got them all, is d dx f of x, or df dx, or dy dx. So these are just weird, aren't they? Or you can put a big D in front of the function and say that's what it is. I'm taking the derivative of that function. We do this in differential equations. Or if you're taking derivatives with different letters within the same problem, sometimes you may be taking the derivative with respect to another letter. Sometimes you have to write d sub x and then put it in front of the f of x. So the ones that you'll see mostly in this class happen to be this one right here and this one right here. Now sometimes we'll see this. Okay, so I better circle this one here. Sometimes we'll see that d dx. Okay, and so this is just notation. Let me explain this notation right here. So some of you might want to skip forward through this if you don't want to see why do we have this notation, sometimes called Livens notation. Well, remember where the derivative came from. The derivative came from this right here, f of x minus f of t all over x minus t. So what we have right there is average velocities within a time interval. Well, remember what the derivative was. It was the limit as x and t get closer and closer together, or x approaches t. Okay, so it's rise over run, really. And so you won't be doing this in your homework, doing this derivation here. This is the limit as x approaches t. Well, really, f of x minus f of t, those are y values. So that's a change in the y. And in math, when they say change in y, they'll sometimes use that triangle. Change in y, delta y. And then those are x values, or those were times. But we'll call them x values. That's the change in x. So we are taking the limit as x approaches t. Change of y over change of x. And that's perhaps why or how this notation came to be, because once you finally take the limit, you have a dx. Let me actually write this another way here. This is really the limit, because there's no t there, and that was bugging me, as delta x approaches 0 of delta y over delta x. Okay, and so that's why, once this approaches 0 and the limit goes away, that's why we have this notation dy dx. Okay, so there it is. There's going to be another explanation that I'll give you about the dy dx, but for now, lots of times you might read a book and they might say, well, this is where it's kind of coming from, and this is the limit of delta y over delta x, which then, once you finally take the limit, we can call it dy dx. So these are notations that we have to get used to, especially the ones that I circled for this class. We'll get into this one later as well. The f prime and the y prime, by the way, the prime is usually the one that people feel the most comfortable with at the beginning of taking calculus. If you just looked at me explaining this and you're like, I don't know what happened, don't worry about that. Just worry about, like, here's some notations for derivatives. The ones I circled will be the ones we see more in this class. Okay, let's go back to our other problem. So we had a function right here, f of x, and we found its derivative. We mentioned that the derivative is really the instantaneous velocity, but it's also the slope function. And this will be the first time I'm going to show you this. I don't want you to be overwhelmed by this, but I'm going to do it anyway. This is a function that can be graphed. It's a rational function. But the derivative is also a function that can be graphed. It's also a rational function. And so I'm going to put those graphs right next to each other, and we're going to investigate that. So there it is. Okay, so you don't have to worry about graphing this here and graphing that there. I'm just giving you the graphs of this. And the funny part about this is, you can take a look at this point right here, which is x equals 1. And, you can put 1 in there, you get 1 plus 2, which is 3 over 3 times 1, so 3 over 3, which is 1. So that makes sense. Now let's look at x equals 1 down here. When you put 1 into this derivative, it gives you negative 2/3. And so there's negative 2/3 on the y-axis. So yeah, that's what that point is. So what does this mean? This means I have to go get my green ruler. Because this is negative 2/3, it describes the slope of the tangent line at that point, which is negative 2/3, which is right there. Let me just do the tangent line maybe in a different color. So it's a negative 2/3, which describes this. Look at the slope here, rise 2 over a negative 3, negative 2/3. And so you can do this pretty much with any point on here. So I'll go ahead and pick another point. Look at this point right here, negative 1. I know this is going to be maybe similar. You put negative 1 in here, you end up getting maybe it's not going to be that similar. You end up getting 1 over negative 3. So its y value is negative 1/3, and that's the way it looks. You see that? So if you put negative 1 into this, it gives you negative 1 quantity squared. So this is going to give you negative 2/3. So the I picked one that was the same thing, didn't I? Oh well. So it just says the slope at this point is also, the slope of the tangent line at this point is also negative 2/3, which would actually be parallel to the other one. So I just went ahead and picked those points. I didn't mean for that to happen, but it happened. And it doesn't mean the slope is always going to be 2/3. So we better pick a third one now. So look at this. I'm going to pick 2. So 2 plus 2 is 4. 4 over 6 is 2/3. Now that's not the slope, that is the y value there. So the y value there is 2/3. And it does look like that, see, up on the y-axis. Now if I go ahead and put 2 into the slope function, it will describe the slope of the tangent line right there. So if I put 2 in there, what do I end up getting? So I didn't really plan on doing all this, so hopefully I'm not going to say the wrong thing or write the wrong thing down. But here it goes. 2 in there, so 2 squared is 4. 4 times 3 is 12. Negative 2 over 12 is negative 1/6, which means, and I'll put this tangent line in a different color, negative 1 over 6. There's that tangent line. That's the green tangent line is tangent at x equals 2 on that graph. And it does have a slope of negative 1/6 because, well, maybe I didn't draw it. 1, 2, 3, 4, 5. Maybe I should have drawn a little better. Okay, so it's not going to be perfect. Maybe I should have, actually, it should have been, I don't know what it should have been. But I drawing these lines, I mean, that might not be a perfect tangent line, but that has slope of negative 1/6, and this thing told us that. Now look at this. This is going to be kind of cool. The top graph has a horizontal asymptote at y equals 1/3, so it's kind of going above the x-axis. But what is the slope of that tangent line right there? The slope of that tangent line almost looks like it's 0, and there it is. But it's a negative. It's slightly negative. And then look what happens as I move along that graph and I look at the tangent line. Okay, the tangent line there is negative, but it's really close to 0. But then as you start moving along this curve, the tangent line, like right here, we said it was what? Right here we said it was negative 2/3. But if we keep moving along this graph, so I'm moving here along this graph, along the original graph, maybe this guy right here is negative 2 for the slope, and there's negative 2 right there. And then as you keep moving along this graph, what is happening to the tangent line? Its slope is getting like negative 13, negative 100, negative 1,000,000. The slope is going like that. Also, like when you come on the other side of this vertical asymptote, you have a slope that is like negative 1,000,000 there, and so that's down there. And then as you start walking along this graph, the slopes are all going to be negative, but they're going to get closer and closer to 0, aren't they? Until you're like right here, it's very close to 0, and so is this. This describes the slope. Okay, so this was sort of an introduction to looking at a function and its derivative and showing you that the y value of every point on here describes the slope of the tangent line for the corresponding x value on the original graph. And that's what I'm trying to show you. We'll get better at this. So if this kind of flew over your head, let's talk a little more about slopes, and that's what we'll be focusing in on for most of this section, is the slope of graphs. So let's see if I can find the next problem that we're going to do. It does upset me that I could have probably drawn this green line a little better, but I was trying to draw it fast. And then we had a smear mark there. But like I said, if I was a super perfectionist, I'd still be working on the first video for this class, and that would really suck. Okay, so look at this. At which points is the slope of the curve negative? So this is a different curve. This is a brand new problem. This is an example, so I'll put EX. And let me just mention that negative slopes, like those three red, those two red lines and the green line, they have negative slopes. Negative slopes, when you read them from left to right, go down. Positive slopes, when you read them from left to right, they go up, because positive slope, you'd go rise and run, and you'd be going in the positive direction for the rise and the run. So let's take a look at this. At which points is the slope of the curve negative? At which points is the slope of the curve positive? Why don't we go ahead and try to draw the tangent line at each point. So this one right here looks like it's the bottom of the valley. So let's, kind of looks like that. That looks like the tangent line there. Let's do E next. This tangent line looks about right there. This tangent line, it's kind of hard to draw. I mean, you just do your best on this. It's right there. C. We're just trying to draw a line that just nicks the surface there. Right there. And then B. That one's a tough one. Right there. Okay, so at which points is the slope of the curve negative? That means as you read the tangent line, there's 5 tangent lines there. As you read it from left to right, you are going down. And so, like, look at this one right here. This guy right here, as you're reading from left to right, it's going down. It has a negative slope. So this point, point E, has a negative slope. What other points have lines that are going down when you read them from left to right? Well, that would be point D. Okay, so it looks like at which points is the slope of the curve negative? We'd say D and E. Okay, at which points is the slope of the curve positive? That's where the tangent line, when reading from left to right, goes up. So we can eliminate D and E because that's going down, and it looks like B, it's going up, and C, the tangent line, is going up. So we're going to put that for our answer for part 2. B and C. Now you might be wondering, well, what about the tangent at A? Well, that's not going up, that's not going down. So we couldn't put it for any of those answers. Okay, it's not negative, it's not positive. The slope on that one, now I'll use the M, the slope on that one is 0. And remember, even though 0 doesn't have a negative sign, and, sometimes people think 0 is a positive number. It's not. It's not negative, it's not positive, it's right in between. So that's why it didn't get put there. So here's the tricky one right here. It says, list the slopes in decreasing order. Okay, so we want the biggest slope first, because decreasing means going down in value. The biggest slope. So your biggest slopes would be the highest positive numbers. So let's take a look at this one right here. We have that guy right there, and that guy right there. So the slope at B and the slope at C. Which one is steeper? The slope at B or the slope at C? Well, the slope at B is steeper, so that's going to be the largest number slope. Okay, I'm not saying it's the steepest slope. It almost looks like D is steeper, but that's going to be a negative number. So B is pretty steep, and then C is less steep. Those are your 2 positive slopes. Now, remember, it's rise over run, so maybe C is like you rise up 1 and you run over 2, and maybe B is you rise up 2 and run over 1. So steeper slopes are higher in value when you're positive. Okay, so now before we start listing off these negative slopes, we should probably then say, well, I mean, this is like, maybe this is positive 2, and then this is positive 1/2. I'm just making up these numbers. And then you need a what? The slope of 0. So that's point A. Now this gets a little tricky because, you know, some of you might be confused. Which one should I put first? I mean, let's just make up the numbers here, okay? I know this is not very mathematical, but I mean, maybe this one had slope of 2 and this one had slope of negative 1/2, or no, what am I saying? Negative 1/2. How about 1/2? Okay, what about these guys right here? Which one's going to have a higher magnitude of slope? They're both negative. It's going to be the steeper one. So maybe this one here has slope of like negative 4. I mean, you're a little bug and you have to go up 4 and then run over 1. So that has a higher magnitude. And then this one maybe is m equals, we'll just guess it. They're not asking for these numbers. We're just doing this so we can get the answer here. Maybe negative 1/2. So as you are decreasing, which one comes next on the number line after 0? Would it be negative 1/2 or negative 4? Well, it would be negative 1/2. So we're going to say E is next. And then the one that is the most negative, or the closest to negative infinity, is point D. And so we have just listed the slopes in decreasing order. In terms of this problem, it helps me to actually draw tangent lines, or do my best to draw tangent lines. And they're not going to make 2 points be so close in slope that you're going to be sitting there going, I don't know, let me measure the millimeters. They're going to be pretty obvious in your homework. Okay, so that happens to be this problem here. Let's go ahead and do another problem. This one's going to probably be easier than the one that we did for the first problem in this lecture, and it's asking us to find the derivative of x squared. Now, it's not going to take long, but we need this because we are going to be looking at graphs, and a lot of the graphs will have the standard parabola as part of the graph. Okay, so we need to have some of this information that I'm going to do down. So what I'm going to do is I'm going to figure out dq. Okay, dq is f of x plus h minus f of x all over h. So f of x plus h, I'm not going to color code this one this time. This is x plus h squared minus f of x. So that's x squared. This is all over h. I go ahead and multiply out a FOIL because this is x plus h times x plus h. So this is x squared plus 2hx plus h squared minus x squared. This is all over h. The x squareds are out of there. And you can factor out, so this is still dq. You can factor out an h on the top. So this is 2x plus h. And there's an h on the bottom. You have one term on the top now. You used to have two terms, but now you have one term on the top, one term on the bottom. We can cancel the h's. So this is 2x plus h. That right there is your difference quotient. And the derivative, f prime, is the limit as h approaches 0 of dq, the thing that we have right there. So this is going to be 2x. So the derivative is 2x. Okay, so here's the deal. We have a parabola. The derivative of a parabola happens to be, what is this creature? A line. That will always be the case. If I gave you any parabola, the derivative would be a line. So let's take a look at the pictures of those two graphs. There are two graphs here. Here's f, which is x squared. Here's f prime, which is 2x. So there's the pictures of those guys. This describes the slope at each point up here. Okay? So we can take the point 1, 1 and say, what's the slope at 1, 1? Well, you can come down here to the graph. There's two ways of doing it, and you can say, oh, well, this graph right here, and let me see if I can, this says x and y. This y-axis really describes the slope. We can call it the m-axis, or the slope axis. And look at this. This point right here is the point 1, 2. So 2 is the slope right there. So let me go ahead and draw the tangent line, and I'll do it maybe in blue this time. And hopefully I'll draw these tangent lines correctly. Okay, so I'm trying to line this up here to... Can't seem to get that right. There it is. Okay, so 2... What did they put in my water today? Maybe it's the green ruler. Well, in any case, that has slope 2. M equals 2. Let's take a look at this point right here. This point is the point 2, 4. Well, we can come down here to 2, 4. Oh, sorry, not to 2. We come down here, here's 2. Actually, this is a coincidence. This guy right here tells you the slope at this point will be what? 4. So it is a coincidence that those are the same ones there, same y values. And so this one has slope of 4. Let's see if we can get this a little faster than the other one. So this is m equals 4. You could also investigate the slope at this point. You find the slope at that point is what? The slope at -1 is -2. So we can put -2 right here. I'll put it down here, m equals -2. And that was this point. And then this point at -2, which is -2, 4, it has a slope of what? It has a slope of, look, the y-axis tells me -4. So, let's see, maybe a color I haven't used, which is purple. So this is -4. We can do this here. We'll try the best to get accuracy. Okay, so this is m equals -4. Okay, remember how I said there was another way of getting those slopes, -4, -2. Oh, look at the slope at this, this is the most important one right here, the slope at 0, 0. Well, it happens to be what? It happens to be the y value of that point is 0. So it's going across there, which is the x-axis. Okay, so I said there was another way of figuring out the slopes without using the graph. And that would have just been by plugging -2, -1, 0, 1, 2 right into that function. I'll do that using a table. So here's x and here's f prime of x. So -2, -1, 0, 1, 2. We put -2 in there. We get a -4, and that's kind of what we got when we looked at the y coordinate there. And then this is -2, 0, 2, 4. And so that would be another way of finding the slopes at those points. Now, just because I use nice integer values doesn't mean that's all it applies for. We can find the slope of this graph at x equals 1/2 or x equals pi. The slope at x equals pi is 2 pi. Like, why would you do that? Well, if you were taking trig, that comes into play more, the pi. So that's the deal. I think the thing I really want you to remember is when you have a parabola, and it's a standard one, and you go 1 and 1, and you hit that point right there, whether the parabola opens up or down, that one's going to have a slope of 1 or a slope, no, not a slope of 1, a slope of 2 or a slope of -2. You'll see as we do some more examples. So some of our examples will have this guy embedded, in a piecewise defined function. And these numbers are worth knowing, okay? Let's go ahead and look at some definitions. So where is my definition sheet? Everything's all messed up here. I started off all organized, but something happened. Okay, look at this. F. Okay, this is a new word. F is differentiable. Okay, F is differentiable at a point A, at A. If and only if, that's what the IFF stands for. If and only if F prime of A exists. Okay, so this is the definition of differentiable at a point, a function being differentiable at a point. The if and only if means you can say if this happens, then F is differentiable. If F is differentiable at A, then this happens. Okay, that's what if and only if means. Okay, so first definition is definition of differentiable at a point. The second definition is the definition of a function being differentiable on an open interval. Okay, think of this as an open interval on the x-axis. If and only if F is differentiable at every number in that interval. So that's what it means to be differentiable on an interval. It's just like a whole bunch of these things are true for every point in there, and so that's what we have. Let's take a look at our next example. This next example is a graph you've probably seen from pre-calculus. It's the absolute value graph. So here's the absolute value graph. It says, what is the slope at x equals 3? So x equals 3, go to the x-axis, there's 3. Put a point there. Can we draw the tangent line to that? Yeah. That's pretty simple because it's right on the line. There's the tangent line right there. The tangent line and that line right there are the same thing, and it has slope. If you do rise over run, 1 over 1, it has a slope. Make sure that I have the right thing up here. It has a slope of 1. Now what if I had said, what is the slope at x equals 4? The answer would still be 1. Okay, so with lines, the slope of that line, any point on that line, at least this part here, happens to be the slope of that line. So what is the slope at x equals 3.5? 1. And what is the slope at x equals 5? 1. And what is the slope at x equals 1 million? 1. Okay, so notice I was putting positive x values in. Now they're going to ask, what is the slope at x equals -3? So here's x equals -3. Well, now the line, the tangent line, if you draw it, which is right there, is actually that part of the line there. You could do rise over run, rise up, run to the negative, so 1 over -1. Slope at -3 is -1. What is the slope at -3.5? -1. What is the slope at -1,000,000? -1. Okay, so on this graph, it seems like if you're a point on this graph, you've got one of two slopes. It seems that way. If you're on the right side, your slope is going to be 1, and if you're on the left side, your slope is going to be -1. But there is a problem point, and it's this guy right here. This is a sharp point. So, wow. I mean, if you approach, if you start doing instantaneous velocities and secant lines and approach from the right, you're gonna say that limit happens to be 1. But if you're approaching from the left and doing maybe average velocities to get an instantaneous velocity, you're going to say the slope is -1. So the right-hand side and the left-hand side do not equal in terms of computing, the limit of the slope, because this one's always slope 1, slope 1, slope 1, slope 1, slope 1, slope 1, slope, and then over here this is slope -1, slope -1, slope -1, slope -1, slope -1, and then when they hit they clash. So we would then say, what is the slope at that? We can say that f is not differentiable, so I'll abbreviate that, differentiable at x equals 0. You're going to find that whenever you have a corner in the graph, and we can call that a corner, that you can't find the slope of a corner. Okay? Because it's so weird. I mean, coming from one side, you're going to get one thing. Coming from another side, you'll get another thing. Okay, so functions are not differentiable at corners. And we'll actually go ahead and put that up on another piece of paper. Okay? Graph f prime. Okay, so this guy right here is f. And then this right here will be the graph of f prime. Well, f prime is really the slope function. So what is the slope at 3? We said the slope at 3 is 1. What's the slope at 4? 1. And what's the slope at 3.5? 1. In fact, the slope at any positive x value will be 1. And you put all those points together, what does that give you? It gives you a nice horizontal line. So that's what I'm going to draw. Now, the slope at 0 is undefined. So I'm going to go ahead and put an open circle there. Now, what is the slope at -3? It's -1. And the slope at -4 is -1, and the slope at -3.5 is -1, and slope here is -1, and slope here is -1. We're talking about the slope of that graph. And so remember, just like in the other problem, we can replace this y with this describes the slope. So the height of this graph describes the slope. So it looks like what you're going to get on the left side of the y-axis is a horizontal line going that way. And there's an open circle there. See, the derivative does not exist at x equals 0. And you can see that the graph does not exist there. And so that is how you answer this question. And we're going to be doing more problems like this where they're going to give us more complicated graphs, and we're going to have to graph the derivative. Okay, let's take a look at our next definition here. Our next definition. It's not really a definition, it's a theorem. F is not differentiable at A, if and only if. So, 3 things can happen. A is a corner. Okay, so a corner looks like that. Okay, and we can see our last example. Okay, I'll put that C last example. I'm going to see if the camera is still rolling. It's going to cut off after a while because somehow when you get your camera at a garage sale, it's not perfect. I try to look at the settings, but somewhere in the 50-some seconds it likes to cut off. A is a discontinuity. We learned about discontinuities. There are actually 3 kinds of discontinuities. Removable, jump, or infinite. A removable just looks like it's a little hole in the graph. Jump is what you think it means. The graph jumps up to another part. And an infinite means there is a vertical asymptote. Okay. And so these are values of x's that where the graph would not be differentiable. Corners, discontinuities, and the other thing would be vertical tangents. Vertical tangents look like this. It's when the tangent looks vertical. So maybe a vertical tangent is like right here. You try to put the tangent line, it's like vertical. Okay? And also vertical tangents can look like this. This right here is sometimes referred to as a cusp. It's still a vertical tangent. A cusp is where the tangents of each side or each branch are the same. Okay? Well, they look the same. There's a symmetry with cusps. Okay, so that's where f is not differentiable, at corners, discontinuities, and vertical tangents. Now, we can talk about endpoints. And is a graph differentiable at an endpoint? Like y equals square root of x. Is the graph differentiable at x equals 0? We're not going to worry about differentiability of endpoints in this class. Okay? So, because there are, we can get more into advanced calculus and we can get more into it, but I think this is going to be enough. So now what we're going to do for the rest of this lecture is we are going to do 4 more problems. We're going to be given pictures of functions and we're going to be asked to graph the derivative. So here's problem number 1. Here's our graph of f. We just call everything f, don't we? And here is the graph of f prime, which we're going to supply. Okay, the first thing to note, so what is the problem here? The problem is to sketch the graph of the derivative, which at first, this looks pretty overwhelming. It looks like, how are we going to do this? Let's see if we can, okay? The first thing to notice is that there are some corners on this graph. There's a corner right here, where it just shifts. You can see that's a corner, and there's a corner there, and there's a corner there. So there are 3 corners. And what do we know about corners? We know that the corners are points at, where the function is not differentiable. Okay, so we shouldn't have graph at the x value -2, 0, or 4. So let's focus in on -7 to 5. Okay, that's the interval, the x interval from -7 to 5. We said we're not going to worry about endpoints and differentiability of endpoints, so we're just not going to include those. Okay, first of all, is your function continuous on that interval? Can you draw function f without lifting your pencil off the paper? Yes, you can. So this is continuous on the interval -7 to 5. And we'll just say f is, or f continuous on that. Where are the points where this thing is not differentiable? Well, at the 3 corners. So let's say not differentiable at. And when we say at, we're listing out off x values. It's not differentiable here at x equals -2. At x equals, what's that x value there? It's 0. And the third x value, where there's a corner, is at 4. Okay, so let's investigate the slope here. I'm going to bring out my slope stick right here. And look at this, like the slope right here, at this point right here, that looks like 0. Rise over run. Horizontal line has slope 0. The slope right there is 0. The slope right there is 0. The slope right there is 0. Look what's happening. All these points from -7 to -2, they're going to have slope of 0. So -7 to -2. Not including -7, so we're going to put an open circle at -7 because we're going to say that it's out of our range. And -2, it's not differentiable at -2, so I'm going to put an open circle there as well. But the slope here, slope 0, slope 0, slope 0, slope 0, so it's going to be a horizontal line right there. So there's the first part of our answer, kind of smeared it there. That's all right. Now, let's look what happens from -2, x equals -2, to x equals 0. Every point on that line segment is going to have the same slope. But what is the slope of this line segment? It's rise over run. Rise, so I'll start right here. 1, 2, 3 in the positive direction, and -1 is what we're running. So it's going to be -3 for the slope of all the points on that line. So -3. So I mean, you could say that this point x equals 1 has a slope of -3. If you like, you can replace that y with an m because this is describing the slope. And x equals -1/2 has a slope of 3. And because it is a line segment, all the x values on that line segment are going to have the same slope, which is -3. So we're going to have another horizontal line. And at the corners, we're going to put open circles. At the corners, your graph is not differentiable. Okay, so maybe I should put f is not differentiable at those x values. Okay, so now we're looking at the x values between 0 and 4. And you can find the slope of that line segment. What is the slope of that line segment? It is rise over run. Looks like it is 1. So from x equals 0 to x equals 4 with open circles on those parts, all those slopes are going to be 1. Okay, the last thing that we're going to cover here on this example is from 4 to 5. From x equals 4 to 5. Well, what is the slope of that? Well, rise over run. Rise, which is 1, 2, 3, 4, 5. 5 over 1. So every point on that line segment has slope 5. So from 4 to 5, I'm going to go up to 5. That's the slope. From 4 to 5, I don't need a ruler for this. There's a horizontal line segment there as well. This right here describes the slope of this function. This is also the velocity function. Okay, though it would be hard to imagine the velocity, you know, the bug's going certain velocity 0, I guess the bug's just sitting there and then instantly goes to velocity of -3, that means to the left, without actually doing anything in between those. So this gets a little tougher when you're analyzing the bug because it has the places where the graph is not differentiable. Okay, so that completes problem number 1, and of the ones after this, these derivative graphs might not be nice straight line segments. So we're going to take a look at the next one. So this is problem number 2. Now in your homework, they're going to have you sketch a few. Some of the problems in your homework are just going to be matching. Those are a lot easier because then you can just like pick a point and say, what's the slope at this point? And then look at the 4 graphs and go, oh, there's only one that has a positive slope or a negative slope. So this is problem 2. Here's the graph of f. And then this will be the graph of f prime. So that is what they're asking us to do. This looks like this graph we're going to be analyzing from negative infinity to 0. This is really what we're analyzing, and then from 0 to positive infinity. So that's what we'll analyze in terms of the derivative graph. And is this graph continuous everywhere? Can you draw it without lifting your pencil? And the answer is no. You have to lift your pencil where? You have to lift your pencil at x equals 0. So this graph is, so f is not continuous at 0. Where is this graph not differentiable? Remember, differentiable, do you see any corners? The answer is no. Do we see any vertical tangents? No, it's getting kind of vertical there, but it's not a vertical tangent. And do we see any discontinuities? Yes, we do see a discontinuity at 0, so we can say that f is not differentiable at 0. Okay, we also see this weird thing. This looks like a parabola, so we'll assume it is, because look, here's the vertex, and you go 1 over and 1 down, you're at a point on there, and then you go 2 over and 4 down. So this looks like our standard parabola that gets flipped and shifted. But this is weird, because you go here toward the y-axis, and then there's an open circle there. And then on the other side of the y-axis, we're coming off a vertical asymptote. So that's kind of unique. So let's see if we can graph this thing. We'll graph this part first, this parabola. So the easiest slope on this parabola happens to be where the slope is 0. So the slope is 0 right at what x value? The slope is 0 right at the x value of negative 2. So I'm going to go ahead and put a point right there at negative 2. Remember, this describes the slope. Okay, let's go right here, this point on the parabola. Now if we remember our parabola thing, remember our special numbers for our slopes were like 0, 2, 4. So, what do you think the slope at this point is? Well, it's positive. Draw the tangent line, and because it's from that standard parabola, we'll make a guess that it is 2. So at negative 3, the slope is 2. And if you're kind of confused, like, where did this come from? 2 tells you the slope. Look, here at negative 3, the tangent line has slope 2. And at negative 4, so look, we go 1, 2, and then we go 1, 2, 3, 4. We have a slope right here, which is steeper. It's still positive. And if you look back at that other example with the parabola, you'll see that we can say that the slope of that is 4. What do we also know about the slope of a parabola, or the derivative of a parabola, happens to be a line? So do you see that these guys all lie in the same line? We could say, well, what is the slope at x equals negative 1? That's going to be negative 2. So we can put a point right here. And if this one existed, if there was a point there, well, it would be an end point. We don't want to worry about that. But let's just say if there was a point there, it would have a slope of negative 4. I'm going to put an open circle there at negative 4. And to describe the slope of this part of the parabola, I'm going to draw the line. And so the line goes like this. There it is. Okay, so that takes care of this part, of this parabola part. Let's go analyze the slope of this now. Okay, so this is where we can't be super precise, you know. So if you're like, I want to be a perfectionist about this, it's going to be really hard. You're going to get frustrated. What's happening to this slope as you are actually traveling to the left? The slope, look, the slope is going like this. So look, that might be negative 13, negative 15. It's a negative slope. Negative 100, negative 1,000. Negative 1,000,000. Where is that slope approaching as you are getting closer to the y-axis? It's approaching negative infinity. So we believe that when we do the slope thing, we are going to have the slope graph going toward negative infinity as you travel closer to the y-axis. So it's going to then travel like this. It's going to come like this, and it can get less and less in magnitude. See, look, negative 1, it maybe is right there, and then this is like negative 1/2 and negative 1/3, and I'm traveling along this graph here. So like if the bug is right there, then this is like negative 1/10, and then over here is negative 100, and then over here is negative 1/1,000,000. So where's that going as you are traveling on the x-axis, as you are investigating the slopes? The slope's getting closer and closer to what? It's getting closer and closer to 0. So that's what this graph should do. It's always going to be negative there. Everything there is negative, but it's going to get closer and closer to 0, to the x-axis from below. Now, because we don't want to sit here all day and like, let's draw a line and analyze this. This is not a parabola. It's going to be curvy. It's not going to be a nice line, but we're not going to spend forever pulling our hair out saying, how precise should I be? This is a rough sketch of the derivative. So we're just going to go like that, where there is a horizontal asymptote, and there's also a vertical asymptote right here. I could draw it right there, but it only applies for this part. And so that right there, this is a rough sketch. Not so rough on the line segment, but let me write this down in case you're looking back at this later. This right here is a rough sketch of the derivative. And let's do a few more of these problems. It'll get a little more interesting. Oh wait, that's the one I want to do. Wait, what's happening here? Yeah, that is the one I want to do, and this will be number 3. I should have actually labeled them before the lecture. So there's number 3. We're going to be investigating from negative infinity to infinity. Do we see anything that, well, first of all, let's talk about maybe continuity. Is this graph continuous? Well, the deal is, it's not continuous at one point, one x value. It's not continuous at x equals 1. So we're going to say f not continuous at 1. Okay, what else can we say? What about differentiable? Where's f not differentiable? F is not differentiable. So I believe on the first problem I was saying where f was continuous, but I think maybe it's better to say where f is not continuous in some of these problems. F is not differentiable. Well, at the discontinuity of 1, but there's another place where f is not differentiable. F is not differentiable in 3 places. Discontinuities, which we have one of them. Corners, I don't see any corners, but vertical tangents. And look what happens as you follow the slope of this graph. Right there at 0, 0 is a vertical tangent. So f is not differentiable at 0 and 1. Okay, let's see if we can draw this graph. This is going to, let's see how tough it is. Maybe we can do the easy part first. So what is the easy part? The easy part is this, they call it a ray in geometry, where there's a point and then it goes off this direction. It's like a half a line or whatever. And so what is the slope of every point on this line here? Well, the slope, if you do a tangent line to any point on the line, it looks like that. It's horizontal, the slope is 0. So what we're going to do is from x equals 1, and I'll put an open circle there because it's not differentiable there, I'm going to make a horizontal line, and it's actually going to be on the x-axis. So there it is. Okay, that was the easy part because that was a line. Okay, so now what are we going to do? Well, look what happens here. This guy right here. So we have to just imagine, like, what is this thing? This thing has a negative slope, correct? And if I filled in that point, the slope would be like what? About -1. So all we're doing is rough sketches. So at -1, I'm going to go ahead and put an open circle. I'm actually traveling to the left. And then what happens at -1 as I travel up to that vertical tangent? What's happening to my slope? It's getting steeper. It's getting more negative, higher magnitude of a negative number. I mean, that right there is -10. And I just made that up, by the way, but it's like -10, -100, -1,000,000. So where's the slope going from this? The slope is going, like it did in the last problem, down along the y-axis. So I'm going to draw that. Now, should I make it a straight line or a curve? I'm going to make it curved, and I'm going to make it go like that. And what happens right at x equals 0? That's where the vertical tangent is, and we can't have that. We cannot put that on our graph because it's not differentiable. So this is the graph of f. This is the graph of f prime. Then what happens as you go to the left of 0? Then what is your slope? Your slope is a very big negative number, or a negative number that has big magnitude, like this right here is -1,000,000. And then we're traveling along this. So -100, -2, -1, -1/2, and you're going that way. So the graph is also, in terms of the slope, really big, and it's coming down like this. Now, where is it going as you're walking off to the left? This slope, this blue line, is starting to become more and more horizontal, so it's getting closer and closer. It's always negative, but getting closer and closer to where? To slope of 0. Remember, this right here is slope, so look what's going to happen here. This is going to get closer and closer to the x-axis. And we saw something like that in the last problem, where there was a vertical asymptote right here. We can actually do the whole thing on this. And then there's also a horizontal asymptote, which is the x-axis. And I'll stop it right there because I don't want to put it on there, and it only applies for when the graph is going toward -infinity. And so that is our rough sketch of the derivative. Now, if you're like, man, I really hate this, we're not going to be doing rough sketches of the derivative throughout calculus. This is the one time I think we do something as crazy as this. We're going to do our last example, which is example number 4, and we're going to see what this thing gives us here. So this is number 4. We are analyzing things from -6. So I don't include the -6 because I'm not worried about endpoints, all the way to infinity. Well, actually, it excludes -7. So, I mean, what could I say? We'll go like this, and then 7 to infinity. So that's what we're looking at. Okay. Where is this graph, if we start off at -6, where is this graph not continuous? So f is not continuous at what x values? When would you have to lift up your pencil to draw? Well, at x equals -2. Where else would I have to lift my pen up? Oh, at +2. Okay, and then I'd have to lift it up, and now I'm drawing here. And when would I have to lift my pen up? Oh, right here at 7. That's a removable discontinuity, and the other two are jump discontinuities. Okay, so it's good to figure out where the thing's not continuous, because it kind of helps. Once again, this is the graph of f. So I'll put it right here, f, and then this is f prime. Okay, let's look at where the graph is not, f is not differentiable. F is not differentiable at these discontinuities, but is there another place where f is not differentiable? Well, at these corners. Look, there's a corner there and there's a corner there. So I would have to put 0 into this list here, and also 5. So -2, 0, 2, 5, 7. So when I draw my graph of f prime, I better not have graph at any of those x values. Okay, we kind of already knew 7 wouldn't have a graph. Okay, let's go ahead and draw our graph. This time I'm just going to go from left to right. This looks like a semicircle. Now let's look what happens with the semicircle. Now if there was a full circle and you drew a tangent line to a point on that circle, wouldn't the tangent line be vertical? So right there you've kind of got a vertical tangent, and if you just move slightly to the right, now your tangent's like a trillion. Okay? So what we're going to have at -6 is a vertical asymptote. So this is x equals -6, and if we go a little to the left of it, it looks like the slope is very large, positive number. Here's the slope. So it looks like I'm coming from up there and I'm coming down like that. So let's continue to see what happens. Look at the slope here. I'll try to put my hand where you can see this without knocking over the tripod. Look at the slope. The slope there is 1. And then look what's happening to the slope when we get to that top of the circle. The slope right there at the top of that circle is what? It is 0. Which x value does that happen at? That happens at x equals -4. So I'm going to put a dot right here. The slope is 0. So it looks like this line's going to come down here, go through that point. Now what's happening? Now I've got like slope of -1/2, so it looks like it's going to dip below the x-axis. -1, -2, -3, -1 billion right there. And so there's going to be another vertical asymptote at the x value of -2. Okay, and you're going to be at -1 billion. You're going to be down here. So I'm going to go ahead and this is a rough sketch, kind of go like this, and say that describes the slope of that semicircle. I think that was the hardest part of this problem, and I decided to do that one first. Let's continue. What is the slope of this line segment? The slope of that line segment is -1. So from x equals -2 to x equals 0, you're going to put a line segment, open circles here, at -1 for the y value or for the m value. That's what that looks like. Okay, now let's investigate the graph between x equals 0 and x equals, that's a 2 there. X equals 0, x equals 2, that has slope of 1. So between x equals 0 and x equals 2, I'm going to put a slope of 1. It's going to be a constant horizontal line because all those points have slope 1. All these points have slope 1. Okay, now look at this right here. This is the next part, and that looks like a parabola. Look, here's the vertex. You go 1 over, 1 up. You're on the parabola. You go 1 over, 1 up, and then you go 2 over and 4 up. So this is good. At x equals 3, that has a slope of 0. So at x equals 3, I'm going to put point right there. And then this guy at x equals 2 has a slope of, looks like a negative slope. We're going to say -2 on that one because we studied the parabola. So I'm going to go at +2. It looks like we said that had slope of -2. So I'm going to put a point at -2, but it's going to be an open circle. Why? Because f is not differentiable at 2. And so we know the parabola, the derivative of the parabola is a line. So let's continue at x equals 4. That looks like the slope is 2. And I'm getting that number because we studied y equals x squared. And then at 5, because look, we go 2 over 4 up. So at that point, it looks like the slope is 4. But I'm not going to put a closed circle. I'm going to put an open circle because at 5, it's not differentiable. And then I have a line segment. So that, this guy right here describes the slope of that partial parabola. Okay, so this is really not going to be that bad now because all these points have slope of -1. The only problem is at x equals 7, so I'm going to go ahead and put open circles at x equals 5 and x equals 7. And I'm putting them at -1 for the slope because that has -1, just like this one had -1 and we have that. So let's go ahead and finish up this graph. That right there. That right there. Whoops, I'm moving this around too much. And so, wow, this was a little tough looking at graphs and doing rough sketches of the derivative. That is our last problem from 3.2. You guys have a good day, and I'll see you in the next video.